Welcome to the fifth session in the second module in the course on signals and systems. We will continue from where we left in the previous session to talk about how we could deal with a phase change intelligently when we have a sinusoidal input. Recall that a phase change was the problem as compared to a magnitude change in a sinusoid. The phase change did not result in a pure multiplication of the sinusoid by a constant independent of time, if one dealt with the sinusoid in its primitive state. But if one considered the sinusoid as a combination of two rotating complex numbers which we call phasors rotating in opposite directions, you could focus your attention on any one of those rotating complex numbers, effect the change of phase there, and then deal with both of them together. Let me illustrate this by taking any one of those complex numbers. So, let us consider one phasor. Let us call that phasor a e raised to the power j omega t plus phi. Now, let us make a phase change of delta phi, which means we have a e raised to the power j omega t plus phi plus delta phi. Now, this can be rewritten as a e raised to the power j omega t plus phi multiplied by e raised to the power j delta phi. And this is the important thing. A change of phase is just a multiplying factor, albeit a complex multiplying factor. That is not really our problem, but it is just a multiplying factor, and that is why we could, in the context of electrical circuits, R, L, C circuits, treat the voltage current relationship as constant independent of time if the excitations were sinusoidal. So, you could look at one of those rotating complex numbers. Now, let me come back to this particular phasor here. You see, if you look at it, in this phasor, we have a e raised to the power j omega t plus phi. Here, you have anti-clockwise rotation. Now, let me take the corresponding complex conjugate phasor. So, let me take the what we may call the complementary or complex conjugate phasor, which of course would be a e raised to the power j omega t plus phi, the whole complex conjugated, or a e raised to the power minus j omega t plus phi. And here again, let us effect a change of phase. Now, the important thing is that when we make a change of phase of delta phi here, so let phi be replaced by phi plus delta phi as before, we would of course get a e raised to the power minus j omega t plus phi plus delta phi, and this is essentially a e raised to the power the original phasor multiplied by a e raised to the power minus j delta phi. As you notice, this is essentially the complex conjugate of the previous constant. So, the beauty is that if I have the same change delta phi in the phase in the two cases, in one case the corresponding constant by which the original phasor is multiplied is the conjugate of the other. So, I need to look at any one of them. In fact, let us look at the sinusoid, underlying sinusoid as we call it. So, if you take the underlying sinusoid here, which we could write as, well, a cos omega t plus phi. Now, you see, the beauty is that you could write this as 2a e raised to the power j omega t plus phi plus e raised to the power minus j omega t plus phi divided by 2, and that is a e raised to the power j omega t plus phi plus a e raised to the power minus j omega t plus phi. And here, now I could make a change of phase in this sinusoid. So, let us change phi to phi plus delta phi. And what is the change that occurs? What we have seen. So, here this is then multiplied by e raised to the power j delta phi, and this one by e raised to the power minus j delta phi. So, in short, what I am trying to bring out is that if I make a change of phase in the underlying sinusoid, then it is reflected as a multiplying factor in both of the phases which come together to form the sinusoid, and I need look at only one of those phases to understand the effect of change of phase, which is just a multiplying factor. The other one is just the complex conjugate. The multiplying factor for the other phasor is just a complex conjugate. So, I do not need to worry about that too much. So, the work involved is not very different. I could have dealt with the original sinusoid, here I am just dealing with a phasor. It is so much more mathematically convenient to deal with the phasor both for amplitude changes and for phase changes. And even though there is one more phasor rotating in the opposite direction, I do not need to deal with it explicitly. If I deal with one of the phasors, what is happening to the other phasor is known automatically. This is the beauty of phasors. And now again I am emphasizing that is why we allow complex signals and complex constants in our discussions in signals and systems. You recall that I had postponed the reason for this when I talked about allowing complex signals and complex constants in the first module of the course. I had said that we have to allow complex signals and complex constants, and now we understand the reason why. When dealing with the very ubiquitous sinusoid, it is convenient to deal with the corresponding phasor, a complex signal, as opposed to the original sinusoid as it is. Well, so much so. Now, the next question that we are going to ask is, what happens when you put a sinusoid through a linear shift invariant system? We have seen that sinusoidal signals have a special place in our minds for various reasons. Now, suppose I have a linear shift invariant system, and for the moment let us make our life easy by assuming the system is also stable. Well, why am I saying the system needs to be stable? Because the sinusoidal signal, sinusoidal input is bounded, and if the system is stable, at least I am guaranteed the output is going to be bounded. So, I do not get into trouble in that sense. So, let us assume we have a stable linear shift invariant system, and let us see what happens when I put a sinusoid into it. So, here we go. So, sinusoidal input to a linear shift invariant stable system. Let us assume that I have this linear shift invariant stable system S script S here, and let its impulse response be ht. Now, of course, the LSI system is stable. Assume ht is real and S is stable. We will see how it plays a role. So, I have here the input 2a cos omega t plus phi being given to the system, and we question what is the output. Now, by itself, of course, I know that I could use the convolution integral. Let me write down that convolution integral. So, output by convolution, the input xt is 2a cos omega t plus phi. The impulse response is ht. Of course, ht is absolutely summable, absolutely in fact integrable to be more precise. Let us find the output. The output is going to be yt, and here I will use this form h lambda x t minus lambda d lambda, which is minus infinity to plus infinity h lambda 2a cos omega t minus lambda plus phi d lambda. Now, you see, all that I can say from the stability of the system is that yt is going to be bounded. But beyond that, if I look at the expression here, this integral as we see it, no sense can be made out of how I might simplify this integral. It is very difficult to simplify. So, it is not going to help for me to deal with the sinusoid as it is. In the next session, we shall see how we can do much better if we just think of the sinusoid as two rotating complex numbers of phases. Thank you.